Hello. Oh, thank you. I'll go ahead and introduce myself. My name is Michael Starch. I am a flight software engineer at JPL, which means I do a little bit of embedded computing, a little bit of software computing, and a little bit of tinkering with cross-compilers and toolchains. So this talk, first we're going to say a little bit more about myself. Then I will go into an introduction of some of the foundational concepts. This talk comes out of an experience I had a couple of years ago when I was trying to set up embedded systems experience for a bunch of users running on a bunch of different systems. And so I'm not approaching it from the seat of an expert who knows everything that's going on, but the seat of somebody trying to learn this information and slamming my head against the wall over and over and over again. And so come on in, we've just got started. So it might not all be 100% pinpoint accurate, but it's my experience, and I'm trying to guide you past all the mistakes I've made and get you to the place where you can repeat the work I've done and have much more success than I had a few months ago. So we'll come through some of the introductory material. Scale has a lot of students and other people running around, so I wanted to make sure to cover what are the concepts I'm talking about, what is cross-compiling, all of that. Then we're going to talk about a lot of solutions that just don't work, but seem like they should. And this is the big confusing point that I had, is there's a lot of starting places that you say, oh yeah, that's obviously what you do, or at least that's what I said, was that's obviously where you start, and it's just plumb wrong. And so we'll go through those. We'll talk a little bit about what's actually going on, which will explain and illustrate why all of these various solutions fall apart. Finally, I will give you one workable solution, and we'll have a conclusion. And now I am really nervous because my friend Joseph just walked in, and I'm sure he's far more talented at this stuff than I am. Sorry, Joseph, I just had to say hi because I haven't seen you in a while. Anyway, please join us. We're just getting started. This is the agenda for the talk. All right, I'm going to talk a little bit about myself. First of all, I have a picture of myself holding a large rocket. Why? Because it's a cool picture. And it's a little bit different and sets the tone for this talk, which is we're not going to be super formal. We're going to have fun and dive into the details of embedded systems engineering. Yes?
Did you ever have to explain this picture to somebody, some talk that showed up unannounced?
No, but I've presented this to people way up the stack at my workplace, and they just kind of looked at it and were like, okay, great. So apparently nobody's afraid about a picture of me holding what looks like a missile, but is actually a rocket. As I said, I'm an embedded systems engineer. I do spacecraft control software. I work primarily in C++ with a little bit of C, and that's the foundation of this talk. I took the C++ cross-compiling stuff out and threw it away so that we could focus on C. The concepts I want to explain in this talk today really don't matter if you're doing C or C++, and C++ is an extra level of confusion that we don't need to get at the what is going on features. I'm also the community manager of the F-Prime software framework. It's a framework for building embedded systems, and it's designed to be cross-platform. That is the software I was working with when I encountered all of these issues. And it works on inexpensive hardware. And then finally, I am a longtime scale enthusiast. I work on the AV team. We keep all of the cameras running. So just as we're here, everybody say, thank you, AV team. They've been working since Tuesday night, basically nonstop, keeping the streams running, YouTube up, so that you can view these talks offline, and so that all of these nice slides and audio equipment work correctly. They're all volunteers. If you happen to see somebody in the shirt, like that black shirt in the back of the room with the little penguin on it, say hello and say thank you, because they are really working hard. All right, let's jump into the talk. All right, so first, what is C, what is GLIBC, and what is GLIBC? Because when I first started working with these systems, I kind of got that all conflated. So C is a programming language. I've had you all raise your hands. It seems like most of you know what C is, but C is a programming language, and it's one of the first, as they would say, high-level languages. Before C, lots of people worked in assembly, and that level where you're very tied to the hardware, you're doing very specific instructions for very specific machine hardware, and then people started inventing what's known as a high-level language, which is a language you can write that theoretically can work on multiple different machines, and a tool takes that high-level language and compiles it into these machine-specific instructions so that you can run on your Raspberry Pi ARM or this x86 laptop and have basically the same code base. We all know that that's not quite true, but for the purposes of this talk, we will say that C is cross-platform, high-level language. And so that introduces the idea that you can use C on embedded systems. So an embedded system is a computer that is stuck somewhere that is not a standard, laptop with keyboards. So that camera in the back of the room is an embedded system. It's got a tiny little computer on it that hosts a web server and a bunch of other stuff. And there's a few other embedded systems in this room. You could argue that this phone is an embedded system. There's probably an embedded system in that projector. I think most of the people in this room know that, but again, I'm trying to cover the basics so that if anybody is brand new here, we can come up to speed. In order for C to provide high-level features for your particular project, it needs a library of functions. We've all seen printf and various other functions in C that we call. These functions are implemented in what's known as GLIBC. It is the C library that your code can link against, can call into to get the functions that you need to build your programs so that you're not back to writing every single instruction and poking every single register. It's built on top of your OS's API, that's assuming you're running an OS, and it's supplied by your compiler. So essentially, when you compile for C code, they give you an implementation of the C library supplied by your compiler that links into your OS and knows how to poke the OS to do things. So rather than calling, say, the open function on file descriptor 0 so that you can run printf with the write function, they give you printf, which does all of that stuff underneath. That's what libc is. So then what is glibc? Because glibc is that thing that has been screaming at me for 15 years out of compiler error codes. glibc is the GNU C compiler, GCC that is, implementation of libc. So that's the one that ships with GNU. And so you can see over here, remember, C is the language, libc is the library, and GNU is the specific implementation designed to work for Linux of the C library. That's how all these pieces fit together. Does that sound reasonable? Does everybody kind of follow what I'm saying? Great. So, moving on, what is cross-compiling? I know this may seem like novice work to most of you. I've been cross-compiling for a while, but the first time I heard of it, I was like, well, why would you care? So the idea of cross-compiling is I have this nice laptop that can build code really fast, but it runs on x86. And my nice Raspberry Pi there, for this demo, we're using Raspberry Pi 1. And Raspberry Pi 1 runs an ARM chip. ARM is a 32-bit operating system, 32-bit bus width architecture that has a specific ARM instruction set, whereas my x86 laptop has a different instruction set. And we can talk a little bit more about instruction sets and what they mean when we get to the end of this talk. For the purposes of cross-compiling, the computer language, the machine language that my laptop speaks, is not the same as the Raspberry Pi, but the Raspberry Pi does not have the build oomph to compile that my laptop does. So I want to build code on my laptop and put it on my Raspberry Pi. Make sense? Now, why would you use this? Because as somebody said at the very beginning of my talk, well, you can just build on the Raspberry Pi, right? It's got Linux, it's got GCC, you can SSH in and build there. Why would you want to do this? Well, in my world, with spacecraft, often you can't just SSH onto the spacecraft. You have to build a binary and then flash it onto the hardware itself to get up and running. So quite often we find ourselves cross-compiling for our target hardware and not being able to just build on it. It doesn't have the power to build, or it doesn't have the compilers and things installed to do the build. So we're cross-compiling all the time. Extrapolate a little bit on my test hardware, the Raspberry Pi, which is my spacecraft in this case. I like to cross-compile for it because then I'm building the skills I need when I get to the real complicated stuff. So that is cross-compiling. What is our testbed and what is the problem we're looking at today? Cross-compiled code can crash. This is one of the most annoying things, but your cross-compiled code can crash. And this can be because you have incorrect tools, incorrect libc versions, and we see some of these errors down here at the screen. So now I have to step across. I've tried to highlight them, but they're still a little small. This error here is the bane of my existence. glibc 2.34 is not found. Another area that you can see, I don't see it very often, but is illegal instruction, and finally, execution format error. Those 3 errors are the ones we're going to be digging in today and see why the various approaches to getting software built on my laptop doesn't work on the Raspberry Pi. A little bit about our test hardware. I'm using a Raspberry Pi 1B. I installed Debian from 2015. Why? Because it's old. And old is one of the major problems that I run into. And then finally, our GLIBC version is 2.19 compared to this error that you see here, 2.34. We'll dive into that a little bit more. I used the Raspberry Pi 1 instead of the Raspberry Pi 4 or 5 because it's old. The whole purpose of this talk is cross-compiling can cause issues. And if you use super new equipment, a lot of these issues silently disappear. And we want to see why they appear so that we can fix them in our own projects. All right. We're going to start talking about some solutions and why they fell apart. But are there any questions about the test hardware that I used to build this talk? Yes?
Why not just use something like Q user mode for testing before you actually ship to the hardware?
So why not use QEMU user mode before I ship to the hardware? QEMU, for those of you who don't know, is an emulation platform that allows you to emulate different processors. You absolutely can run QEMU and emulate those processors, and if you're emulating a processor and a whole operating system on top, you'd see these same errors. Why didn't I do that? Because I looked at setting up QEMU and I looked at the Raspberry Pi in my box ready to go and said the Raspberry Pi will be faster and my goal is to build this talk, not necessarily futz with QEMU. But I did start looking into QEMU before I made that decision. Yes?
Plus, there's also the fact that sometimes the QEMU emulation of your target isn't close enough of an emulation.
Yes. So QEMU models can lack various pieces and aren't always a perfect model of your hardware. Yes?
Well, I want to add cynicism to that. Once you start adding physical hardware to the platform, different I/O peripherals, video cards, now your QEMU is completely irrelevant because it's just running a kernel.
Yes. So there are lots of trade-offs with QEMU. For the kind of presentation I'm doing here, we could have used QEMU. Again, for this presentation, it was just faster because I had the Raspberry Pi, I had the Debian version already, and I said, I can get that up in 5 minutes, and QEMU, I haven't used enough to be that efficient with it. But it was a speaker choice. All right, let's move on to some solutions. So the first solution is just compile. Run standard GCC just like you do on the command line, GCC compile, and then ship it to the hardware. This does not work. And the error you see when you try to do this is execution format error. The question is, why doesn't this work? Well, we already talked about this a little bit. My laptop is speaking x86 instruction sets. Give me just a moment. x86 instruction sets are a CISC instruction set that comes out of Intel and AMD processors typically designed for laptops, where my Raspberry Pi is ARM 32-bit. They're different machine languages. They talk to different registers, they use a different assembly language, and so when you run GCC on the laptop, it is building what you see down here, an ELF 64-bit for the architecture x86 64. That means it's designed to run on an x86 64-bit processor, and it's in 64-bit mode. It will not run on my ARM. And so when it gets to the ARM, you get that famous executable format error, which says, this was compiled for a different architecture. You speak a different machine language than I speak. That's why it does not work. But this is the place where most people start with cross-compiling, is they start building on their computer and just copying code around. Maybe you were smart enough to sidestep this, but you can imagine starting here. So what is this really for? GCC, in this way, is for your local machine. It's for building on this particular laptop, downloading code that you want to run here and building it locally. It's compiling source for local use and building testing locally. There's a question here and here, so go ahead in the back because your hand's raised. So that's a good question. What is actually running the error? So I'm not an expert. I don't know for sure, but my understanding is that there is give me just a moment. There's a language interpreter that is a shared library for Linux. It's not GCC, it's Linux, and that's the ELF loader. And so when it sees this application, it loads the ELF file, inspects it, and says, oh, this is wrong. Does that? Is that LDSO? I believe so, yes. And so go ahead.
Yeah, so and if you do a full static And if you do that, then it's just from a kernel, I believe it's a kernel kill signal, like it says.
Yeah.
But it gets sent with enough information to print exec format here.
Yeah. And so if we have some time at the end of the talk, we can pull up LDD and start looking at some of these libraries and see the things that are going on. But you're right, ld.so is the piece that is launching the interpreter of these ELF signals and trying to run them. With a entirely static build, you can remove these pieces, but then you get a different error. In the end, if those machine instructions get to your CPU, it's not going to work because they're the wrong language. And so there are pieces built into the system to prevent that. You had a question earlier.
They probably mostly answered it. I was just trying to make sure I understood exactly what GLIBC dynamic was. Is it like the result of a link? Is it
Oh, what is this line? So this line here is the name of my executable. So I made a little makefile that just chugged through these executables, and I've named my executables. This is glibc. That is, I'm compiling with glibc, the purpose of this talk, and I'm compiling in dynamic mode, which means I've linked it as a shared object.
So it's the output of your link.
It's the name of the executable. So it's, yeah, the output of the link step, precisely. And we'll see a little bit more as we go on. These names will become a little bit more clear. Any other questions here? Cool? Oh. All right. The next thing that I tried is running a distribution or prepackaged cross-compiler. What is this? So Ubuntu, in their package manager, ships a cross-compiler for ARM 32-bit. And I said, that's got to be it. You can also download some packages from ARM that have these cross-compilers in them. And so I said, this is obviously the solution. I just install the package on Ubuntu, cross-compile, and go, right? Apt install, that's the name of the apt install package that I tried, and it didn't work. This version is packaging a very specific version of glibc. So as you can see here, we didn't get the executable format error. We've got the right format. That's why this is blue. We've got the ELF 32-bit for ARM with EABIS. And our version is glibc 3.4. As we said at the beginning, our test hardware runs glibc 2.19. And so what has happened here is we've built an executable with the correct machine instructions, but because we have a different version of glibc in our compiler, it does not work. What has happened is our executable depends on a version of glibc that is too new. And this is the error that cost me a month of time trying to debug, because I was still operating in the mode that the packaged compiler from Ubuntu was the right answer, and there was something else wrong. And the real truth of the matter is, my version of libc on my embedded software was just too old, and so I couldn't run the new prepackaged cross-compilers. What is this actually for? Why did they ship these ARM packages in Ubuntu? Well, the answer is, it's for building for this distribution on another architecture. Ubuntu ships multiple packages. I'm talking about Ubuntu, but lots of Linux systems do this. You can run Ubuntu 22.04 on this laptop and 22.04 on my Raspberry Pi 5. They want to build the same packages for the same version of Ubuntu. Well, in Ubuntu, they're going to ship the exact same version of libc, the exact same version of the kernel, and the exact same version of these packages. So these cross-compilers really are intended for compiling from Ubuntu 22.04 to Ubuntu 22.04 to produce those missing ARM packages so that anybody running Ubuntu can use them. And why is this not a problem? Because across the Ubuntu sphere, on a version of 22.04, all the versions match. The version of the compiler, the version of libc here, and the version of libc there. Yes, go ahead.
So that at least at first glance, you need to get the one that says none there rather than Linux there.
So there is no none there. The Linux there says we are running with the Linux operating system. So if you want to talk a little bit about that name, GCC, that's the compiler. ARM means the architecture. Linux means not none. None would be no OS, bare metal. But instead, we're running for Linux. And then GNU EABIHF is talking about the specific architecture. So in this case, we're using glibc, GNU. EABI is the ELF format, and HF means hard float, which my Raspberry Pi has.
So that was the confusion, because on Debian does distribute GCC, ARM, none, GNU, EABI.
So They may distribute none on Linux too, but again, that's for cross-compiling to bare metal, where you don't have libc in the mix. You're just compiling without an architect or without an OS. And so the goal here is to compile from one platform to the same platform on a different architecture. So Ubuntu 2204 to Ubuntu 2204 ARM. Make sense? This extends to downloadable ARM packages too. They have a bunch of ARM compilers that are pre-built out there, therefore compiling for that version of ARM that has the built-in libc version. Did you have a question? Ah. So the question was, are we depending on the libc version on the target because we're dynamically linking? And the answer is yes. And you have jumped ahead a few slides because we're using all of these red herrings to figure out what's going on, and you've kind of figured it out. On the target, there is a libc version. So let's jump ahead a little bit. This is what's going on. Our Hello World program runs on a libc, versioned libc on the target, and then hits the Linux API underneath. And so we haven't really gotten to the Linux API part because we skipped a few steps. But that's exactly what's running on your target here. And then we'll talk about how all of this works between the computer and stuff when we get to that point. But let's cover sysroot first. So sysroot is another option for cross-compiling. Sysroot allows you to say, well, here's a system root. This is the actual system I'm compiling for. Here's all that stuff on the file system. It looks, it has /etc, /bin, /lib, etc. Go build for that so that you can build for the exact target. And when you do this with the sysroot flag in GCC, you get the same error. Why do you get the same error? Because sysroot doesn't override libc. It overrides every other library, allows you to link against any other shared object or archive file, but for some reason, libc is still built into your compiler. So despite the fact that this program here, glibc sysroot dynamic, linked against a shared object that I had on my system root, it still picked up the wrong version of libc and compiled with that same wrong version of libc. But again, we've still got the right object format. And yes? So that's the other problem with sysroot is you have to construct one. I did an SCP of the file system, I believe, off the SD card. So I plugged it into my SD card slot, read it over. I don't necessarily recommend this approach because it's complicated to set up and very difficult to get right. Removes a lot of files, and you still have the wrong libc version. So what is this for? This is for a quick and dirty build where you want to link against your own shared objects and libraries that aren't libc. So you're still dependent on the same libc, you're still kind of in the same versioning space, but you have other libraries that you want to use, like a library from a vendor or a library for a camera or something that you've installed on your system root. For example, through a package manager that you want to clone over so that you can do a cross-compile into the environment you expect. But again, you're still expecting your libc versions to work. All right, static linkage. Static linkage is the last thing I tried, and this is the idea that you take all your code and you jam it into one binary. There are no more dynamic loaders, there is no ld.so, there is no glibc.so. You cram it all into one big beefy binary that has all the code inside. And then in this way, you're avoiding the shared libraries, you've removed the versioning problems, theoretically, and it still breaks. So what did mine do? It produced a segmentation fault. Great. So now my code is segfaulting, and all my code does is say print. It's not very complicated. How does it segfault? Well, what's going on here is we've hit the Linux API, where libc is now compiled into my binary. You are now dropping into the Linux API below libc, and the Linux API says, well, I can build in the Linux mechanics, but the Linux kernel is different on my target computer. So now the Linux over here is expecting data structures to be one way and memory to be organized one way, and what you compiled with has a different expectation of what Linux is doing. Because again, you compiled it on this host with a newer version of libc and a newer version of the Linux kernel and said, oh, now I'm trying to write structures in a new format that doesn't work. So even though it's speaking the same machine language, it's not speaking the same kernel language, and so all those data structures in memory in the kernel just break. So we've gotten libc out of the problem, and we still ran into a versioning problem. Isn't this fun? So we talked a little bit about what's going on. I jumped ahead to help guide this speech, but let's go through it again. You've got your Hello World program. My program that I tested through all of this is literally Hello World. It runs on top of libc, which has a version, and that libc version expects a versioned Linux API, so that the data structures that are the kernel, that are running in memory on your target, are the data structures that the API expects and can interact with, which are then the API functions that libc expects, and then all of that version stack gets pushed up into Hello World. So in the end, to successfully cross-compile, we need to get libc in order, we need to get Linux API in order, we need to clarify the versions and provide them all to our program so that everything runs and there aren't any whoopses, I didn't get that version quite right, or that structure isn't quite right, or that function call isn't quite right. You had a question.
Well, actually, I'm guessing that what's happening in this case is that since your Linux on the Raspberry Pi is older than probably what's on your workstation, that it's trying to use system calls that weren't defined yet in that old version of Linux.
So it depends. It's in the dynamic versions, it's trying to use system calls that don't exist, and it's running into the problem that either the C library or the Linux API are out of date. In the static version, we crammed all that code together, so it's not an old version, it's that the data structures, at least this is my understanding, the data structures in Linux changed. So the way they organize memory, the way they provide certain functions are all based on a runtime kernel, and that runtime kernel is slightly different. So even though the code should all be compiled in, it doesn't mean the structures in memory that the code is interacting with are the correct version.
And it may be thinking that system calls exist that don't exist on your old Linux.
Again, oh yes, system calls, yes, that's possible. Yeah. And so what is actually going on? This is actually going on. So you have your Hello World program that ships to your compiler, which has a version of glibc and a version of the Linux API it expects. It's running on top of your host OS, which has a different version of libc and GNU, and then sitting on top of a different version of Linux. I'm assuming you're compiling on Linux, and all of this stuff bounces back and forth and causes the failures that we've seen. The static or the straight compile fails because you're on that third version of libc and Linux. The built-in prepackaged cross-compilers and the static compilation fail because this middle version of libc is out of date, and none of them match the target compiler. So let's talk about some solutions, shall we? All right, so a workable solution. I came up with a workable solution. I investigated several. Like I said, I have a few spare slides that we can go through if you'd like to see more solutions, but those are a little bit more complicated. So I came up with one good working solution, which is crosstool-ng. Crosstool-ng is a tool that builds cross-compilers. And what it allows you to do, if you go into the configuration, is set your Linux version and your glibc version. And so you can see, I picked the version of glibc 2.19. That was what was running on our Raspberry Pi. I picked the version 4.1.49 for my Linux kernel, because that was the closest without going over version of the Linux kernel that was running on my Raspberry Pi. So I configured just those two properties, and I think I set in the C library, I wanted to use libc and not some other C implementation, and I built my compiler. And it went and churned along, and then it created a binary directory that had a GCC cross-compiler in it. I ran that cross-compiler, and now you can see it worked just fine. You see Hello World there, and you see the right version. What we did was we took a cross-compiler, and we put in the specific versions of things that we wanted to use, and we did this. We cut out the host OS, we moved the compiler and the target versions of libc and the Linux API together. So now the compiler is speaking the exact same versions as the target, meaning libc is in check, Linux is in check, and our executable worked very effectively. So that's the solution I was able to get to work and run on my Raspberry Pi with almost no effort. Crosstool-ng is fairly easy to use and run. So, conclusion. glibc version not found, site fault, and illegal instructions are caused by the cross-compiler and toolchains. it's that versioning mismatch problem that we just saw. Many of the solutions that I tried are error-prone. They seem like the simplest solutions. Install a package that is just download and go. Install something from apt. Just run your cross-compiler. And none of them seem to work. Then I'm like, you got a static link because that'll pack it all together. That doesn't work either. I've ran into all of these faults and realized, oh, this is a lot more complicated. So what you really have to do in the end is make sure that you roll your own cross-compiler for your target that bakes in the Linux version and bakes in the CLib version that you're using. Yes, go ahead.
Out of curiosity, did you ever try going back to the Debian version that you downloaded from the Raspberry Pi and the Debian archives or something and try to get an old cross-compiler?
So yes, that's exactly what I do. You remember that framework that I told you about that I have to provide for many users? In order to make this easy and not have to host my own toolchain somewhere and say, download this, I just found a very old version of the ARM compiler that had a version of GLIBC older than the one on most of our target hardware. Because most people are running a Raspberry Pi that's brand new or some other embedded Linux system that's new. So I just went back to, I think it was GCC 10.3. And that had an old enough version of libc that people stopped posting errors on my GitHub. It's not the best solution. As we just saw, if somebody comes to me with a Raspberry Pi 1 and says I got Debian installed 10 years ago, it's not going to work. But so far, none of my users have tried that one. And so it is a viable solution to just grab an old cross-compiler from ARM or an old version of Debian, but it's not a perfect solution because if you're working with a lot of different platforms, one platform could always be older. But that's a great suggestion. That's actually what I run in practice because building my own tool chain and providing it to my users saying, hey, build with this, that's a lot of hosting and a lot of expectation on exactly what their system looks like. So I picked a solution in the trade space that is a little bit different. How are we doing on time? I have how many? 12 minutes. Okay. So I'm just about where I like to be for questions, which brings us to questions. Perfect. Go ahead. How did I diagnose the segmentation fault and syscall issues? So first, I did a Stack Overflow request and said, hey, what about cross-compiling libc? And there's a giant page on Stack Overflow with a lot of detail, and I read through it and summarized it and then made an educated guess. So I read through all it and said, oh, there's more here than just glibc. It's what glibc is built on, which is the Linux API, which also has a version. And so I just kind of did an educated guess that that's the issue. Now, it could be a completely different reason that it's segfaulting, but it will be a versioning issue of some kind. And the Linux API version changing on you could cause an error similar to a segfault or some other one of these hard to diagnose errors. When I GDB'd it and backtraced it, it was segfaulting before it got to the main function, which is pretty clear indication that something's wrong at the libc version level and not in my code. Did that answer your question? Great. Any other questions? Yes?
Yeah, I was just wondering about the pilot flags for the Arch and so forth. I mean, could you use your tool chain without applying a whole bunch of ARM 32-bit minus F,
Yes.
minus W, blah, 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 that sort of stuff? Or did you just copy that out from someplace else and apply all those compile time flags and options to the compile?
I believe I did. I think I just ran it without those flags. There may be settings in that cross-tool-ng that allow you to put in the default flags, because when you build GCC, it ships with a list of default flags that you can then override. I didn't dive too deeply into that, because my goal was to get anything working at all to show you that this is a viable solution, even with really old hardware. But explore the menu. There are probably 100 menu options that I didn't look through because I found the 2 version ones that I really cared about. And I think my room monitor is going to help us out with the microphone so that other people can hear your question.
There are other situations where you can run into problems similar to like this, but without it being a separate computer. For example, some of my users are big fans of something called Conda, which is a package where they basically are building a Linux distribution on top of a Linux distribution, for better or worse. Because it's compatible with some package they also run on Windows. And so it turns out that anything that runs under Conda was built using a Conda-specific version of GCC and a Conda-specific version of the runtime libraries. But quite commonly, whenever people first are learning Conda, they don't realize that, and they'll do something like build it with the distributions version of GCC and link it to the distributions version of GLIBC. And the worst part of this is that this will often, the binaries will often run for a fairly long time and then abruptly crash with a totally bizarre error message. So if your users use Conda, you have to make sure that they're not mixing them.
That's a great point. So let's backtrace and take the same philosophy that we've had in this talk and figure out what's going on. So we got all these cross compilers. We now don't have a target, but we still have a distribution in this case. Conda is Python, and Python ships C libraries that make Python a little bit faster. So NumPy is built on top of C libraries, and SciPy is built on top of C libraries.
It ships its own GCC.
And it ships its own GCC. So when it builds those packages, you get a version of the output that is a specific version that runs then in part of the Python framework. And then if you compile with a different version of GCC, you have a host GCC and a compiler GCC version mismatch. And even without this target over here, the Python environment crashes. I did the same thing with Rust yesterday. I was trying to work on some of this AV equipment, and I had a Rust plugin that I built on this laptop and just copied and pasted it to another machine, and Rust blew up because underneath Rust was libc linkages, and I compiled with a 2.new version of libc. So you don't necessarily have to be in the embedded world to see these issues. Were there any other questions? Yes, go ahead.
So I saw on an earlier slide when you were talking about statically linking, you ran into an illegal instruction exception. Did you end up figuring out why you ran into that? As far because the segmentation fault at least makes sense that it was a Linux API or the kernel API problem, but illegal instruction indicates something a little more
What was the
close to
illegal
the hardware.
instruction? So the difference between these two is this one was using the Ubuntu cross compiler, the one that comes out of the package version, and then doing a static compilation. This one was the one I downloaded from ARM. So it's failing in different ways because the Linux API versions between the Ubuntu version and the ARM version are different. They ship different versions underneath the compiler. Why one triggered a segmentation fault and one triggered an illegal instruction, I'm not 100% sure. Yes? This is supposed to be ARM 6, because it's the Raspberry Pi 1, so it's an ARM 6 device, and you have to compile it with a bunch of flags that specify ARM 6 and not ARM 7. Say again?
Was that an ARM 6 compiler?
That also could be it.
Okay.
I was
Illegal
still
instruction.
experimenting with all the ARM flags
Okay.
to make sure that it would compile and run on the Raspberry Pi 1. If I had done a Raspberry Pi 2 or 3, these problems would go away because the ARM instruction set is changing on us too. Go ahead.
Yeah, as far as I know, all of the ARM hard float compilers are the same regardless of ARM version. So that was probably part of it, because I know one of the issues I've had is trying to move binaries over from different instruction sets. Like I was trying to set up Ceph on my Proxmox nodes, and some of those nodes are old enough that they don't have SSE4. And yeah, which, you know, nowadays that seems crazy, but these things are only like 9 years old, which it's still new enough that I'm using them. But that's one of the things where I ended up trying to compile Ceph without SSE4, and it never ended up working. But yeah, that was definitely one of the interesting things, is even when not compiling, you know, cross-architectural, you still have these issues of having to compile within an architecture but different extensions, where even if I try and, you know, compile on one system as no SSE4 and then move it over to another system, maybe I have glibc issues, maybe I have Linux API issues, maybe I don't, and it just turns on some other instruction set I don't have.
So that is a good point. I do want to caution users, the Raspberry Pi 1 and the Raspberry Pi 0 ship ARM v6, which does require additional flags. Everything newer runs with ARM v7 and works just fine until you get to the 64-bit stuff, assuming you're running the 64-bit operating system. But we have had trouble with the Raspberry Pi 0 and 1 using just the standard stock ARM compilers. Even if the versions work out, the feature sets are slightly different, and so you need a lot more flags put in that we weren't aware of. And if you build your own cross-compiler, those flags can be built in. There's a question back here.
Yeah. So since you're statically linking the glibc version in, is there anything stopping you from statically linking that in and then trying to run it on a distribution of Linux that doesn't use glibc?
So
like say it uses like muscle or something, right? Where
that's
it's
a good question. So typically users go the other way. And in fact, you've just segued into my backup slides. The pictures on the backup slides aren't so great, but I wanted to run through these before I let you go because these are other solutions you see out in the world. One is a vendor supplied toolchain. If a vendor supplies hardware and they supply a distribution for you, you get a toolchain. Use that toolchain. It comes with the versions built in, you don't have to build your own. Why did I not put this as a working solution? Because a lot of vendors like Raspberry Pi and a lot of these cheaper Linux systems don't supply distributions and toolchains because they expect you to SSH on and compile there. And so they supply the compilers natively. And so not every vendor has these. A lot of vendors I work with don't, which is why building my own toolchain was a better solution. We also had an alternate version of libc. This is kind of what you were dovetailing into. You can choose a different implementation of libc. There's a couple. You mentioned muscle. I'm talking about new libc. And this solution allows you to get rid of the glibc problem entirely and get your own version of libc. Now, new libc doesn't build super well for Linux because it's not designed to run on Linux. It's really for a bare metal system. So you want to run libc-based programs, but you want to do them on a system without an operating system. You can build new libc. It builds pretty well, builds pretty easily, but again, it won't run on embedded Linux, which was the core of this talk. It doesn't really even build for embedded Linux. It kind of hems and haws and then doesn't build anything, and I didn't push it. You can build with muscle, as you said, muscle C, and try to get around these problems, but you still have that Linux API version problem that you have to be careful with. Okay. I was looking into it, and that's when I ran into the ARM flags version problem, and I didn't dive deeper because I couldn't sort out the ARMS flags for my muscle C cross-compiler. I got the cross-compiler to work, I just couldn't figure out which flags would not segfault. And then finally, Yocto. So if you want to go this deep, you can build your very own kernel for your target hardware, and if you build your very own kernel, it will build a cross-compiler for you, and then you can use that and create your own vendor-supplied distribution, but you're the vendor to yourself. I didn't go this route because this is a lot of work and could be a talk on its own, and I wanted to explore what was going on with all these versions rather than diving headfirst into how do we build a kernel for another hardware and configure these tools. So those are the three solutions that you could try, and they have different trade-offs. Go ahead.
I was just going to say it's next door, but there's another solution called NixOS.
Okay.
If you use Nix, you can, it provides a cross-compiler out of the box for about like 30 different architectures. Mostly newer ones. Of course, it's up to each package if it really works that well, because you can have issues where cross builds will actually need to use random binaries during the cross-compilation process, and so it's up to each package if it'll actually work. But a lot of the solution is you can actually export the headers from your target kernel, so you don't have to rebuild the kernel. You could just repackage it and then use those kernel headers in your cross build. But there's a lot you can do there, and if you have a build system like Yocto or Nix that sets up a proper 3-stage cross-build process, it starts to make a lot more sense, and these errors start to fit into proper categories of why they occur.
So, just as a note, I think we're hosting the first NixCon in the United States here at Scale this year. So if you're interested, there are lots of Nix people around. I can't give you a lot of insight there because I haven't used it yet, but there are plenty of people around. So I'd say seek them out. They will have better expert guidance than I do. Thanks for sharing. That's a good point.
Oh,
go ahead.
When you were trying sysroot as a solution to the problem, I should mention that if you try going that route, and I'm not claiming it's the best thing to do, but GCC has, what is it? I forget the name of the command line parameter exact, something like no default libc or something of that sort. And then you won't have the business of the libc on your host machine being pulled in when you don't want it to.
Yeah.
You also have to then go in and add in a few .o files that you normally wouldn't have to even know were there, though.
Yeah, so the .o files that's being referred to is there are a few .o files that are automatically linked against your binary that do the startup work. They start to construct what I learned in school was called the C virtual machine, but it's the stack and the heap and all those bits. So they go from nothing to here's a memory space that your C program can run in. And as part of your work, the GCC compiler does that as well as linking against libc, and if you turn off the default libc, as you said, then you lose all of that too, and now you have to figure out which .o files you need to construct the C universe to run in at all. The reason I really don't like sysroot is some compilers accept the flag and some compilers ignore the flag, and it's all about the flags that were used to build the compiler you were working with, and so that solution is just not stable enough across the different compilers I've seen to really trust it. I think we're about at the end of the talk. I will hang around for a few minutes in the back of the room if you all have questions, but I want to thank you for attending and thank you for the engagement that you've given me. I love an audience that is willing to explore a topic with me, and that's exactly what you've done. Please enjoy Scale, and if you see an AV person, go ahead and thank them.